Transformations of quadratic functions. Like linear functions, quadratic functions can have different positions on the graph. They can move along the x-axis, they can move up and down the y-axis, they can have a different shape altogether. They can get narrower or wider. It doesn't matter the shape of the quadratic function. Each of them can move along the x-axis, up and down the y-axis, or change their shape depending on their values. We said a quadratic function is expressed as ax squared plus bx plus c. The shape and the location of the function is dependent on these coefficients here. C determines its position on the y-axis. That means where it moves up and down the y-axis. B determines the position on the x-axis. That means where its roots are here on the x-axis, and A determines the shape of the parabola. That means it determines if it's going to be like that or if it's going to be very wide. So this is like a little bit like video control game. Depending on the value here will determine the shape of the parabola. The B value will determine where it is positioned on the x-axis, and the C value will determine where it is positioned on the y-axis. Let's look at that closer. Here we have a graph of x to the power 2. We can write it as ax to the power 2, and we know a is its coefficient, and this coefficient determines the shape of the graph. Let's add 2 more to see this better. Here we have 2x to the power 2 and 3x to the power 2. So you can see our first one had a coefficient of 1, our second a coefficient of 2, and our third a coefficient of 3. The higher the coefficient, we can see the narrower the graph. The nearer it is to the y-axis. We can say the higher the coefficient, the tighter the curve is to the y-axis. We can write a coefficient determines the shape of the graph. The higher the coefficient, the tighter the curve or the graph is to the y-axis. We can see the higher the coefficient, the greater the rate of increase. We can see the lower the coefficient, the broader the graph is. So the coefficient tells us how quickly the curve is rising, and it also indicates the shape of the curve. Now let's have x squared plus a constant. In this case, we're going to call it b. We have x squared. The lower one is x squared minus 2, and the upper one is x squared plus 3. We notice that the constant, the b value, determines where the curve is going to be on the y-axis. When we have no constant, the curve cuts the y-axis at 0. And we can see when the constant is 3, the curve is 3 units up on the y-axis, and when the curve or the constant is -2, it cuts the y-axis at -2. So the constant determines where the curve crosses the y-axis. We can say b shifts the function up or down the y-axis. Here we have a function x plus h squared. We have x squared, x minus 3 squared, x plus 2 squared. This h value shifts the function left or right along the x-axis. So here we can see if h is greater than a 0, the function shifts left. If h is less than a 0, the function shifts right. So here we've got x to the power 2, and this one is x minus 3 squared, and this one is x plus 2 squared. So we can see here our blue function, it has shifted 1 to 3 positions right. H was negative, H was less than a 0, so it moved in the opposite direction, it moved in the positive direction. On this function, we can see that H has a value of -2, but it's shifting 3 units left, so it's shifting in the negative direction. So we can see that depending on the value of H, the function shifts in the opposite direction. Now, something to note here. These are expression squared, which means they're only always going to have one solution, meaning they'll only touch the x-axis once. They will never cross the x-axis, they'll only touch it once. So we can see, depending on the value of our coefficients, it will determine the shape of the function and the position of the function on the x-axis and on the y-axis.